In this video, we'll look at what happens when multiple events happen in a row. Let's go back to our jar of gumballs. Imagine that you reach in to pull out a gumball at random and check what color it is. And then, here's the key detail, you put the gumball back. Then you pull out another gumball and take note of its color. What's the probability that the first gumball is red and that the second one is blue? We already know that the probability that the first gumball is red is 5 out of 10, 0.5. What about the second gumball being blue? Well, since we put the first gumball back, the jar is in the same state now as it was before. So the probability that the second one is blue is still 3 out of 10, 0.3. This is an example of what we call independent events. Since we put the first gumball back, it has absolutely no effect on what color we get for the second gumball. It's as if the first one never happened. Think of it like when you roll a die. It's often said that the dice have no memory, which just means that because you rolled a particular number on one turn, that doesn't make you any more or less likely to roll that number again on your next turn. Anyway, here's one reason we like independent events. They make finding AND probabilities easy, because all you have to do is multiply the two individual probabilities together. Since the first gumball is red with probability 0.5, and the second is blue with probability 0.3, if we multiply those, we get a probability of 0.15, 15%, that the first gumball is red and the second is blue. And this works anytime A and B are independent events. The probability of A and B is just the probability of A times the probability of B. Now, what if we'd asked the probability that the first gumball is red or the second is blue? In this case, we'd need to use our addition rule. Probability that the first is red plus probability that the second is blue, but then minus the probability that the first is red and the second is blue. That's to prevent overcounting. But since those two events, the first being red and the second being blue, are independent, when we get to that last AND part, all we need to do is multiply 0.5 and 0.3. And so we get that there's a probability of 0.65, 65%, that the first gumball is red or the second is blue. Now, why was it so important that we put the first gumball back before we pulled the second one? Let's take a look what would happen if we don't put it back. And suppose we ask the same question. The probability that the first gumball is red and the second is blue. Just as before, the probability that the first gumball is red is 5 out of 10. But now, when we try to get that blue gumball, things have changed. We no longer have 10 gumballs, but 9. So now there's a 3 out of 9 chance that the second gumball is blue. This is actually an example of something called a conditional probability. We'll go further into that in the next video, but the main thing you need to know now is that drawing the first gumball now has an effect on the second gumball afterward. So this time, if we multiply our successive probabilities, we get 15 out of 90, which comes out to 1/6, a little over 16%. And that's a bit higher than the 15% we got when we put the gumball back. So knowing whether you're sampling with or without replacement can have an effect on your probabilities. Let's do one more example to tie everything together. Suppose we take out 3 gumballs, one after the other, and once again we'll replace the gumballs after we write down the color. What's the probability that we get at least one blue? This seems like kind of a hard problem because there are so many cases to consider. Since it's saying at least one blue, that could mean we get exactly one blue, or 2 blue, or all 3 blue. And they could have happened in any order. So we'd have to add up all of those individual probabilities for those cases. But there's an easier way. What if we considered the complementary event? What's the opposite of having at least one blue? That would mean that none of the 3 are blue. And that's actually a lot easier to calculate. On any given draw, the probability that the gumball is not blue is 7 out of 10. So since the draws are independent since we're replacing it each time, the probability that all 3 are not blue would be 7/10 times 7/10 times 7/10, which comes out to 0.343. Now, if we flip that back to the original statement, the probability that at least one gumball is blue is just 1 minus the probability that all 3 are not blue, which gives 0.657 as our probability. This is an example of where the complement rule really shines. Sometimes to find the probability that something happens, it's easier to first find the probability that it doesn't happen. Now here's something to chew on. What if we did the same problem, but this time we didn't put the gumballs back? Now what's the probability that you get at least one blue? See if you can use what we've talked about in this video to figure it out.